Okay, so we have discussed about this frequency shifting property, right. So that was the end result that we have got in the last class. So basically what we have seen that if I have a particular signal GT and I know the Fourier pair of that, if I multiply that signal with e to the power j 2 pi f0 t, I get a frequency shifting or frequency translation by an amount f0 t, whichever exponential I am multiplying by. Okay. So basically what happens, the shape remains the same, it just gets translated. So now let us try to see what is the implication of this thing. Okay. The biggest implication is, suppose I have a signal GT. Now let us say I will be multiplying this signal with cos. This is a very typical, actually this is called modulation. Okay. So let us say I will be multiplying by a cosinusoidal signal 2 pi f0 t. Okay. So I am doing this, and this GT is my actual signal probably, and this has a Fourier pair already known, which is GF. So suppose I have a signal GT in time domain and I have a corresponding Fourier pair which looks like this, that is the GF. You see that because it is a real signal, I have constructed the spectrum in such a way that it is even symmetric. So this is the amplitude spectrum I have drawn, correspondingly there will be a phase spectrum probably which is odd symmetric, something like that. Okay. So I have got this GF. Now I know that this GT goes to GF, okay, in frequency domain. Now if I multiply my GT with cos omega ct, what will happen to this GF, how that will look like, how the spectrum of this composite signal will look like. So I have to just take a Fourier transform of this. Okay. Now what I will do, this cos I can write as half e to the power j 2 pi f0 t plus e to the power minus j 2 pi f0 t, right. I can write this. Now because Fourier transform means this will get multiplied, GT into this and then addition. So linear combination, Fourier transform gets distributed. So I can always write half, it should be a Fourier transform of GT into e to the power j 2 pi f0 t plus Fourier transform of GT into e to the power minus j 2 pi f0 t. Okay. Now go back to our previous results. So half, if GT has a Fourier transform of capital GF, then if I multiply with this, it should be GF minus f0, and similarly if I multiply by minus, it should be minus of f0, so that should be plus, so GF plus f0. This is what I get. So basically what is happening, first of all, this GF strength is becoming half and it is getting translated, same G pattern is just getting translated to plus f0. So this is centered at plus f0, this is centered at minus f0. So suppose my f0 is something like this. So what will happen, this whole thing will be little bit reduced and it will be centered around plus f0 and minus f0. Remember, the shape of this spectrum which actually specifies the signal quality, that remains the same. The shape does not change, the spectrum shape does not change. I can again bring it back to 0 and I will get the same thing. So this is in particular a very interesting property of Fourier transform. So what is happening, any signal, if I know the Fourier transform of that, and as long as the signal is somewhat, I should say, band limited, that means now the concept of band limited things will be coming. So what I know about the signal is, if I see the spectrum of the signal, the spectrum or spectral density I should call that GF, beyond some value it either completely vanishes, beyond some value b suppose, either it completely vanishes or diminishes beyond a certain level which is insignificant. Okay. So, then we say that this particular signal, because in time domain we cannot see this particular signal does not contain any higher frequency component beyond some value b. So, beyond b it does not have those components, spectral component. Okay. And then we call this signal as band limited signal, that means it is band limited up to b. So, whatever spectral component it has or frequency component it has, it is limited up to bandwidth b or value, spectral value b. So, beyond b it does not have any spectral component, or I should say any corresponding sinusoidal component. So, if I represent the signal like Fourier series or even in Fourier transform, so I do not get any significant spectral component beyond this particular sinusoidal or exponential, whichever way I am representing. Okay. So, once the signal is band limited, if I try to multiply that signal with a real cosinusoidal signal of frequency f0, where I have deliberately put this f0 to be greater than this b or sometimes much greater than this b, then what will happen, this signal will get translated to that f0. Okay. So, if f0 is not greater than b, then what might happen? So, suppose f0 is somewhere over here, that means the signal is or somewhere over here. So, this signal will be something like this and it will be centered again at minus f0, it will look like this. So, these two things will overlap. So, that is something I do not want. Okay. So, why I do not want, that will be clear later on, but right now we are saying that this is what if happens, this condition is true, then the signal, that particular spectrum part is still as it is. It might be a little bit reduced, but whenever they are reduced, their relative part is equivalently reduced. So, that means the spectral feature or characteristics which defines a signal, that remains the same. So, that relative strength at every point are relatively equivalent compared to this one. Okay. So, the signal pattern remains almost the same. So, what is happening? I am just actually translating them to a higher frequency. It remains, the relative shape remains the same, I am just translating them to a higher frequency. And this particular part is called modulation. Why? Now we can define what is modulation and what is the advantage of doing modulation. Suppose I have a channel. We have talked about channel in the first few classes, and it is a shared channel and everybody wish to use that same channel. So, suppose I want to transmit something on the channel. So, I put some voice signal to my transducer, it converts it into an electrical domain signal, it becomes a voice signal, and then it is being through antenna, it is being radiated into the air, and my corresponding recipient wants to receive this. As long as I am the only one talking to one particular guy, this is all good. But suppose two fellows wish to communicate. Now, after, suppose this is my speech signal, okay, it has a random variation and the corresponding spectrum looks like this. Okay, it will be a band limited spectrum. In speech we say that beyond 3.4 kilohertz there is nothing, all are insignificant. So, it is band limited up to 3.4 kilohertz. So, whatever spectrum component will have, it will be up to 3.4 kilohertz. Okay. So, another guy, so this is my G1T, which is my signal. Another guy wish to also communicate, he also has generated a separate speech signal, a different kind of speech signal. Okay. So, this we call as G2T, which also looks like similar spectrum because it is speech. So, it will still have same kind of frequency component, but it might look little bit, the spectrum might look little different, but it will be almost up to 3.4 kilohertz. Now, if I just superimpose this G1 and G2 and put through antenna at the same time, what will happen? These two spectrum will coexist, and then neither in time domain, because time domain the signal will be just added if it is additive channel, and in frequency domain also the frequency component will be just added. then it is very hard to separate them out, because neither they are separated in time domain nor they are separated in frequency domain. So, I will have no device or no mechanism to separate them out. So, if my receiver wish to now listen, he will get a jumbled signal or a added signal G1 with G2, and that will completely deliver him a completely different speech. It will be just a distorted speech. So, he will not, neither he will be able to listen, neither the other guy who wish to receive G2T will be able to receive. So, that is where if I wish to multiplex multiple users data into the same common channel, I need something else. The device that was designed by the understanding of frequency shifting property is something like this. Let us multiply this G1T with some cos 2 pi F0T or F1T, let us say. Then what will happen? This particular frequency component will go around F1 and minus F1, and it will sit nicely over there. And when we are trying to transmit G2T, we do a separate multiplication with again a cos term, but this time the cos frequency will be different. Let us do it at F2T, where F2 is predominantly different from F1, and this particular signal will nicely be sitting over here and at minus F2. The good part is, now in the frequency domain they have separate location, and at the receiver side what I can do is I can just filter them out. So, there is a device called filter, which most of you are familiar, that just specifically takes some of the frequency, or it just passes some of the frequency component and it suppresses other frequency component. So, if this is the composite signal coming to the filter and my filter is tuned at F1, so what will happen? It is a band pass filter. So, it will just take this amount and it will reject this, whereas the other guy can tune his filter at F2 and he can reject this. So, both of them will get their original signal as if it is transmitted on the air single. As long as we choose this F1, F2 carefully, and as many we wish, we can actually multiplex many, we can have corresponding F3, corresponding F4 and so on. We can actually multiplex multiple users simultaneously, transmitting over the channels, and their separate existence is still remaining because of this frequency translation property. What is happening? Whenever we multiply with cos 2 pi F1T or F0T or F2T or F3T, we know that the spectral component or the relative spectrum, which is the characteristics of the signal, remains the same. It just gets translated to a different frequency band. And all we have to do at the receiver, we have to carefully choose this frequency band, put a filter and extract our own signal and reject all other signal. This is facilitated by this communication technique, or that is why this particular part is called modulation. So, what you are trying to do whenever you are trying to use a media which is being used by all others, you translate or you multiply by a cosinusoidal signal to translate the frequency spectrum into a higher frequency and then actually transmit it in the common media. Everybody will be doing that. As long as they are using separate bands to transmit, they will have separate identity. In time domain it might not have separate identity, but because we have done this, in frequency domain they will always have their own separate identity. That is fantastic. So, this particular thing is called frequency division multiplexing. So, what we are trying to do is, because now you can see all these things are so important, because we have understanding of Fourier series and transform, and because of that we could get another representation of signal, and from the Fourier transform only we could derive that there is a property called frequency shifting property, by which we can actually keep the signal intact but translate it into a higher frequency. And because we have some device called filters which can separate out some portion of frequency, so we can actually give separate entity for separate signal in the frequency domain. So, the entire manipulation is done in the frequency domain. If we would not have understood Fourier transform, would not have understood the frequency representation of a signal, we could not have produced these things. Okay, if we were not able to understand the mathematics behind that frequency shifting property, we could not have produced this thing. So, it is very important, means now you can appreciate it is very important for communication. Any simple technique that has been applied in communication, it is deeply rooted in Fourier series or Fourier transform. It is absolutely necessary that you understand those concepts very clearly. Okay. So, now we have understood some portion of it. We have talked about this modulation, why this modulation is required. We have told that one particular thing is this multiplexing. So, this is now probably clear. We have stated earlier, but now it is all mathematically clear that what we are trying to do and why that is important. There is another aspect of this frequency shifting property or this modulation, that is we have already talked about that whenever you put multiply with cos this one, you can see the frequency component that it is having whenever we are transmitting, it is around f0 some plus or minus. So, earlier it was having, if you just see this one, it was having frequency from 0 to some 3.4 kilohertz. Now, suppose I put them at let us say very high frequency, let us say some 400 megahertz. So, what will happen? It will just go center around 400 megahertz and it will just be around that 400 megahertz, 400 plus 3.4 and 400 minus 3.4. Okay. So, it will be around that 400 megahertz only. So, the frequency component it predominantly had that has been transmitted in the air will be around that 400 megahertz. Whenever it is 400 megahertz the frequency component, the corresponding wavelength will be very short. Okay. 3.4 kilohertz, 1 by that you will see the corresponding wavelength is quite big, whereas 400 megahertz if you do 1 by that you will see because of that 10 to the power 6 it will be very small. And we have also discussed that whenever you are putting a transmitting antenna or receiving antenna, to actually transfer the energy properly, we need to have the antenna size, or to capture the energy properly through the antenna, we need to have an antenna size which is comparable to the wavelength or the corresponding frequency that we are translating or transferring. Okay. So, it is very much essential that the frequency is higher to facilitate the antenna size to be smaller. So, with modulation we are also achieving that particular part, because what is happening here, if you see, there are very small frequency component which will have huge wavelength because it is inversely proportional, and the antenna size will become very huge. Whereas, by just this simple technique, by multiplying the signal with a cos, it serves two purposes. One is it translates it to a very high frequency, immediately corresponding wavelength will be very smaller. So, I can devise very small antenna for my transmitter and receiver, and on top of that we are now creating in the frequency domain multiple such places where we can start multiplexing multiple signals simultaneously and transmit them through the air media simultaneously, and just use a filter to take my own signal and reject other signal. So, that is actually the story behind modulation, you will see that later on. Okay. But right now we are happy with this frequency shifting property which will help us to do modulation. Okay. The next property that we are trying to provide is something called convolution. I am not going to prove that, but I will just state what do we mean by convolution. So, this convolution is given by the star symbol. So, that means a signal is convoluted with another signal, GT is convoluted with another signal, WT. What does that means? Convolution actually means this. Okay. So, what is happening? So, you take this signal GT, okay. Tau is just, do not worry about tau, that is the dummy variable of this integration. Okay. So, take this signal GT, and for omega you can see it is already minus tau. So, basically you reverse this. So, you take omega minus tau. So, like u minus t I was taking earlier. So, take omega minus tau and then time shift it by t amount. Okay. So, do this and then keep varying this tau, multiply this and integrate. So, that is called the convolution. So, basically any signal you take and the other signal you invert it first in time domain and then time shift and keep varying this time shift and you integrate it, multiplication and integration. So, basically one particular signal you will take, that will be, suppose this is my GT, let us say this is like this, and suppose the other one omega t is something like this. Now, what you do first, you flip this omega t. So, from there it will be omega minus t or minus tau. So, this is omega tau, this is g tau. Okay. So, time I am defining with respect to tau, and what you do for a particular, so then you time shift it at tau equal to t, you put it. Okay. So, this will be just at t. Okay. So, whatever that value of t, wherever that t will be, it will look like that. So, at, so this will be omega t minus tau. So, for different value of t, this will, this signal will be going to 0 at different location, and then you multiply these two things and integrate it. So, basically you will be keep on shifting this for different value of t and you will be getting a different value of those integrations. So, this is called convolution, and there is a well known result in Fourier transform. So, I will give this as homework. You have to prove that if I have two signal g1t and g2t, if I convolute them and try to take a Fourier transform of them, if I individually know the Fourier transform of g1t, which is suppose g1f, and g2t, which is g2f, we can always prove that this should be g1f into g2f. So, in time if we convolute, in frequency it becomes multiplication, and if in frequency if we convolute, in time it will be multiplication. That comes from another property of Fourier transform, which is called the duality. So, the duality property, if you wish to know, that is also very simple, we can just very quickly give that. So, we know that GT, I have a Fourier transform which is called GF. Okay. So, in that case what we can write is this GF is nothing but minus infinity plus infinity GT e to the power minus j 2 pi ft dt, right. Now, so this is something we already know. We also know, because it is a Fourier transform, so we can also represent this GT as minus infinity plus infinity GF e to the power plus j 2 pi ft dt, sorry df, right, we know this. Now, what we can do, instead of f, if we just put minus f, so then from this equation we can get GT, I can write minus infinity plus infinity. So, f is replaced by minus f. So, what will happen? This is g minus f, and here we will just get e to the power minus j 2 pi ft, right. So, this is something we will get. Okay. Now, all you have to do is, okay. So, what we have done, we have just replaced this, okay. So, we can do one more thing. Instead of doing it over here, I can also do it over here. So, basically what we are trying to do, I have got this, right. Now, just replace t by f. So, t equal to f, if I just put that. So, what will happen, this GF will become GT and I get minus infinity plus infinity, this becomes GF e to the power minus j 2 pi, f becomes replaced by t and t becomes replaced by f. So, I get ft and t becomes GF, right. So, this is something I get. Okay. So, I get g t is equal to minus infinity plus infinity g f e to the power minus j 2 pi f t d f. Okay. So, now you can see that if I have this as frequency domain, okay. So, this becomes t, right. So, this is almost becoming inverse Fourier transform, but I only have one problem. This there is a minus over here, inverse Fourier transform is having plus. So, what I can do is instead of this f, I can put minus f, right. So, immediately what will happen if f is replaced by minus f, or I can write minus f means minus f as some x. So, immediately what will happen? So, this will become x. So, this is becoming g minus x because it is f is minus x, g minus x e to the power minus, this will become plus because minus f becomes x. So, j 2 pi t x and d, this will be dx minus and plus. So, that will just change the limit. So, this will still remain the same. Okay. So, g t becomes this. Now, you can replace x by f, immediately what you get, our capital G t is becoming just minus infinity plus infinity g minus f e to the power j 2 pi f t d f, right. So, what is happening? Now, I can see this g t and g minus f are Fourier transform to each other. So, g minus f, if I take inverse Fourier transform, I get g t. So, that becomes a Fourier pair. So, basically we have started with a Fourier pair g t which has a Fourier transform of g f. If I just this whatever time domain function I have got, that if I represent in frequency domain, if I just take negative of that, that will have whatever frequency domain function I have, if I just represent it in time domain, I will be getting that. So, that is called the duality of Fourier transform. So, that means suppose I have already got a Fourier transform. Let us say I do a Fourier transform of some this kind of pulse, okay, which is defined from minus t by 2 to plus t by 2. Take that as homework. If you do a Fourier transform, easily you can just put the fundamental Fourier transform these things, you will see that it will be a sinc function, which is defined by this. It is Fourier transform will be g f should be tau sin c pi f tau. Sin c means sine of this argument divided by this argument. So, sin pi f tau divided by pi f tau. Okay, so, the g f becomes this which will be defined as at t equal to 0, it looks like this, at means tau t equal to 0, it is having a value of tau, at 1 by tau it goes to 0, again at 2 by tau it goes to 0 and so on, at minus 1 by tau it goes to 0 and so on. Okay. So, if I already have got a g t which is looking like this, and if I already have got a g f which looks like this, now if I give a sinc function in time domain, that means this becomes capital G t, and if I wish to actually get a Fourier transform, this would be just similar like this. This duality formula tells me that. So, if the frequency domain 1, okay, frequency domain 1 is now becoming my time domain function. So, now the sinc function which was the frequency domain representation, that becomes my time function. This will be just same time domain function will be the Fourier transform. Now, this will be frequency domain. Okay. So, this will be, now this is in time domain, this is in frequency domain. If I take this in time domain, it will just be frequency domain, the time domain 1 becomes the frequency domain 1. Only thing is that it must be having this minus f, but because this function is symmetric over t or f, so it will remain the same. So, they become a Fourier conjugate of each others. That means a square box function if I take, if I do a Fourier transform, I get a sinc function. If I take a sinc function in time domain, if I do a Fourier transform, I get a box function in frequency domain. So, if I know one, I will be always knowing the conjugate of that. So, that is the duality property of Fourier transform. So, with all these basics, what we will try to do is, we will try to now go into the measurement part, which we have ignored. Means we have done that for Fourier series, but for Fourier transform, the measurement part, that means the energy or power, we have still not devised that. So, now we will try to see for a signal, the very important property is the measurement of the signal, which is energy. So, we will try to see how to evaluate the energy of a signal. So, that will be our next target. Thank you.